Imagine a world where bustling cities thrive not on land, but beneath the ocean's surface. For decades, this concept has been the stuff of science fiction. Yet rapid advancements in technology are steadily transforming it into a tangible engineering challenge. For tech enthusiasts, the prospect of underwater cities represents the ultimate frontier, pushing the boundaries of material science, life support, energy generation, and human adaptation. This isn't just about building structures, it's about creating self-sustaining ecosystems where humanity can coexist with the marine world. The primary hurdle for any underwater habitat is the immense pressure exerted by the ocean. At just 10 meters deep, the pressure is already twice that at the surface, increasing by 1 atmosphere for every additional 10 meters. Designing structures to withstand these forces requires revolutionary approaches in material science and architectural engineering. Traditional construction materials simply won't suffice. Engineers are exploring advanced alloys, such as specialized steels with exceptional tensile strength and corrosion resistance, capable of enduring pressures equivalent to hundreds of meters of water. Beyond metals, composite materials, including carbon fiber reinforced polymers, offer high strength-to-weight ratios and superior fatigues. Resistance, crucial for long-term submersion. Transparent ceramics and advanced acrylics are also being developed for portholes and observation domes, allowing residents to view the marine environment without compromising structural integrity. The design of these structures is equally critical. Spherical and cylindrical shapes are inherently more efficient at distributing external pressure evenly, minimizing stress concentrations. Concepts like the Sentinels modules, designed for depths up to 200 meters, exemplify this approach. These modular units are engineered to maintain a stable internal atmospheric pressure, allowing occupants to live and work comfortably without the need for constant decompression. Their robust construction ensures both safety and a comfortable living environment, complete with portholes that offer breathtaking views of the deep. Building at depth presents unique logistical challenges. Shimizu Corporation's ocean spiral concept, for instance, envisions a massive concrete structure, 500 meters in diameter. Concrete, a familiar material, offers excellent compressive strength, making it suitable for resisting external pressure. However, its application underwater requires specialized techniques such as self-compacting concrete or underwater pouring methods that minimize segregation and ensure structural integrity. Beyond concrete, future underwater cities might leverage advanced manufacturing techniques. Large-scale 3D printing using robotic submersibles could allow for the on-site fabrication of complex structural components. This approach could reduce the need for extensive surface-based construction and transportation, streamlining the building process in challenging marine environments. The integration of smart materials capable of self-healing minor cracks or adapting to environmental changes could further enhance the longevity and safety of these deep-sea habitats. Creating a breathable, livable environment beneath the waves demands sophisticated closed-loop life support systems. These systems must meticulously manage air quality, water purification, and waste recycling, mimicking Earth's natural processes within a confined space. The goal is maximum autonomy, minimizing reliance on surface resupply. Maintaining a stable and healthy atmosphere is paramount. Earth factories, a visionary concept, propose using specialized microorganisms on the seabed to convert carbon dioxide into methane. This process, known as methanogenesis, not only removes CO2 but also produces a usable energy source. Complementing this, advanced bioreactors are under development to generate oxygen through the photosynthesis of algae or through water electrolysis, splitting H2O into hydrogen and oxygen. These systems are designed to continuously monitor and regulate oxygen, carbon dioxide, nitrogen, and trace gas levels, ensuring optimal air quality for human habitation. Waste management in a closed system is equally complex. Bioreactors play a crucial role in breaking down organic waste, converting it into reusable resources or inert byproducts. This includes treating wastewater, processing solid waste, and even recovering valuable nutrients. The aim is to achieve near-zero waste discharge, preventing pollution of the marine environment and maximizing resource efficiency within the habitat. Advanced filtration systems, including biological and chemical scrubbers, will remove airborne contaminants and odors, maintaining a pristine internal atmosphere. Access to fresh water is non-negotiable. While undersea docking facilities could provide resupply from the surface, true autonomy requires on-site water generation. Desalination using reverse osmosis membranes is a proven technology, but its efficiency can be significantly enhanced in the deep sea. The higher ambient water pressure at depth can reduce the energy required for the reverse osmosis process, as less external pressure needs to be applied to force water through the membranes, effectively blocking impurities. This makes deep-sea desalination a highly energy-efficient solution. Food production within an underwater city will likely involve a combination of innovative approaches. Offshore fish farming, utilizing controlled environments, and potentially deep-sea water for nutrient-rich aquaculture could provide a sustainable protein source. Plant cultivation, such as hydroponics or aquaponics, within the habitat would supply fresh produce. These systems can leverage LED lighting optimized for plant growth and recycled nutrients from waste streams. Furthermore, the use of deep-sea water, rich in minerals and nutrients, could enhance the growth of certain crops or support specialized marine agriculture, creating a truly integrated food system. Energy is the lifeblood of any modern city, and underwater habitats are no exception. Given their remote location and the desire for self-sufficiency, innovative and sustainable energy generation methods are essential. The ocean itself offers a vast, untapped reservoir of renewable energy. One of the most promising technologies for deep-sea energy is ocean thermal energy conversion, OTEC. This technology harnesses the temperature difference between warm surface water and cold deep-sea water, typically below 1,000 meters, to generate electricity. In a closed-cycle OTEC system, a working fluid with a low boiling point, such as ammonia, is vaporized by warm surface water. This vapor then drives a turbine to generate electricity. The vapor is then condensed back into a liquid using cold deep-sea water, and the cycle repeats. OTEC offers a continuous, base-load power source, unlike intermittent renewables like solar or wind. While the efficiency of OTEC systems is relatively low, typically 3 to 5%, the sheer volume of available thermal energy in the oceans makes it a significant potential power source for large underwater communities. Challenges include the high capital cost of infrastructure, biofouling of heat exchangers, and the need for robust deep-sea pipelines to access cold water. However, ongoing research aims to improve efficiency and reduce costs, making OTEC a cornerstone of underwater energy grids. To ensure energy resilience, underwater cities will likely employ a diverse energy portfolio. Tidal energy, harnessing the kinetic energy of ocean currents, could be viable in certain locations. Wave energy converters, though still largely experimental, could also contribute. For larger, more permanent settlements, small modular nuclear reactors, SMRs, could offer a compact, high-density power source, providing consistent energy with minimal environmental footprint, assuming stringent safety protocols are met. Energy storage solutions are also critical. Advanced battery technologies such as solid-state batteries or flow batteries will store excess energy generated during peak production times. Hydrogen production through electrolysis using surplus electricity could serve as a long-term energy storage medium and a fuel source for submersibles or other systems. The integration of smart microgrids will manage energy distribution efficiently, optimizing consumption and ensuring a stable power supply throughout the habitat. Beyond the technical marvels of engineering and life support, the success of underwater cities hinges on their ability to provide a comfortable, stimulating, and psychologically healthy environment for their inhabitants. Designing for human well-being in an isolated, high-pressure environment is a complex, interdisciplinary challenge. Maintaining a stable internal atmospheric pressure, equivalent to surface pressure, is fundamental for long-term habitation. This eliminates the need for residents to undergo decompression procedures when moving within the habitat, allowing for normal, daily activities. However, the unique environment still presents physiological considerations. The human body's response to prolonged exposure to a confined, high-pressure, even if internal pressure is normalized, environment, and the potential for subtle changes in sensory perception must be carefully studied. Medical facilities within the habitat will be equipped to handle any pressure-related health issues, though these would be rare in a normalized pressure environment. Research into the long-term effects of living in a unique light spectrum, filtered by water, and the absence of natural weather patterns is ongoing. The design must account for these factors, potentially incorporating specialized lighting systems that mimic natural daylight cycles to regulate circadian rhythms. The psychological impact of living in an isolated, enclosed environment is a significant concern. Simulators are already being used to assess the ability of future residents to endure isolation and close quarters for extended periods, identifying individuals best suited for such environments. Habitat design will incorporate elements to mitigate potential psychological stressors. This includes spacious common areas, private living quarters, and access to virtual windows, displaying dynamic surface or marine scenes. Sensory design will play a crucial role. Lighting systems will be dynamic, mimicking natural daylight cycles and offering customizable ambient light to suit different moods and activities. Soundscapes, incorporating calming natural sounds or personalized audio environments, can enhance comfort. Even culinary experiences are being reimagined. Special menus with bold, intensified flavors are being developed to compensate for the potential loss of taste sensitivity that can occur in high-pressure environments, ensuring that dining remains an enjoyable and stimulating experience. The integration of advanced communication systems, providing low latency, high bandwidth connections to the surface world, will also be vital for maintaining social connections and reducing feelings of isolation. Underwater cities are not merely residential concepts. They represent unparalleled platforms for scientific research, resource exploration, and the development of new economic paradigms. Their very existence will drive innovation across multiple sectors. The modular design of habitats like the Sentinels offers unprecedented flexibility for marine ecosystem research. These units can be deployed at various depths and locations, allowing scientists to conduct long-term, in-situ studies of deep-sea biology, geology, and oceanographic processes. This direct access to the marine environment, without the limitations of surface vessels or submersibles with limited dive times, will revolutionize our understanding of the ocean. Researchers can monitor climate change impacts, study new species, and develop sustainable aquaculture techniques directly from their underwater laboratories. Beyond pure research, these habitats could serve as bases for deep-sea mining operations, exploring new sources of rare earth minerals, or for pharmaceutical discovery, investigating novel compounds from marine organisms. The data collected from these underwater outposts will be invaluable for environmental monitoring, resource management, and predicting oceanic phenomena. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.